Pythagorean trig identities, to give them their correct name. Often we just say trig identities, but they're actually the Pythagorean trig identities. Why? Because they all come from Pythagoras' theorem. There's our unit circle again, and I've just drawn in that triangle in the first quadrant with the adjacent being x, the opposite being y. We know the equation of that circle is x squared plus y squared is equal to 1. We also know that if I put it in parametric form, y could be sine theta and x could be cosine theta. Subbing that in, we get the first of the identities. As I say, it comes from Pythagoras' theorem because that's really where the equation of the circle comes from when you think about it. The x squared plus y squared is 1 is the hypotenuse of that triangle. So sine squared plus cos squared is equal to 1, and that actually is the only Pythagorean trig identity. The other ones come from just playing around with this one. If I was to divide everything by sine squared, well then, there we go, I get sine squared divided by sine squared, which is 1. Cos squared divided by sine squared, which would be cot squared. 1 divided by sine squared, which is cosec squared, which is one of the other identities we use. 1 plus cot squared is cosec squared. I could do the same thing. I could divide everything by cos squared. Sine squared divided by cos squared is tan squared. Cos squared divided by cos squared is 1. 1 divided by cos squared is sec squared. And now we have the 3, what we traditionally think of as the 3 trig identities, but as I say, really there is just 1. So there they are, the 3 we tend to use. There also is a lovely little relationship that we use, well, it can be helpful in solving these problems, and that is that sine over cos is the same as tan. Let's play with some of these questions. This first one I bring up because some people do think, oh well, we'll use sine squared plus cos squared equals 1 to work this one out. And I think there's just a much simpler way of doing it. Like they've told me cos theta is 3/4. So I just simply draw up a triangle and say, okay, well, cosine's 3/4, bit of Pythagoras, the other side is square root of 7. I can find tan theta very easily by just reading off the triangle. I don't have to worry about substituting into the identity, playing around with it. So we get, well, it's in the 4th quadrant because they've told me tan is negative, but they've also told me cos is positive because it's 3/4. Therefore, sine theta must be negative, and the ratio is root 7/4. And there's our answer. Some of the more traditional trig identity questions, and first one's very straightforward, but we get something like this: simplify 1 minus cos squared. Now, a lot of times with something as simple as that, you just see it and go, oh, well, there's the answer. But just imagine you didn't, and you've got to think about, well, which trig identity would I use? The nice thing about those 3 trig identities, they all involve different trig ratios, so you can't use the wrong one. So cos squared, and this is going to look like a really strange way of doing it. I'd go, well, hang on, I know sine squared plus cos squared is 1, so cos squared would be 1 minus sine squared. And if I substitute that in, I get 1 minus sine squared. Ah, well, that is sine squared. Of course, the silly part about that is if you looked at cos squared and realised it was 1 minus sine squared, why wouldn't you have just looked at 1 minus cos squared and realised it was sine squared anyway? But theoretically, I mean, that's what we could have done. So sec squared minus tan squared, maybe that one's not as obvious. We go, oh, hang on. Oh yes, I've got a trig identity that tells me that sec squared is the same as 1 plus tan squared. Oh, the tan squareds cancel. I just get 1. Tan theta cos theta, oh, hang on, there's no squares there. So, all right, I'll just change everything into sine and coses and see what happens. So the tan I can change to sine on cos. Oh, look, the coses cancel. We get sine theta. So that's sort of the basic ideas for any trig identity question. If I see the squared, I think about which identity I'm going to use. If I've got no idea, then I'll go, okay, well, let's just change everything into sines and coses and play with it. But now we move to something like this. We're going to prove this particular relationship, that these two things are in fact the same. I'm going to start with the left-hand side and write down what actually is the left-hand side, not LHS. It's a much better solution because you see that, okay, that's what I'm playing with. Sec squared, the trig identity that is involved is sec squared is 1 plus tan squared. Play around with that, expand out. Oh, 2 minus 2. Now I have tan squared on tan. Also got 2 on 4. Cancels down nicely. Now, when you are proving trig identities, how can you approach it? I started with the left-hand side and proved the right-hand side, but of course there's no reason why you can't start with the right-hand side and prove the left-hand side, and sometimes that might be easier. And another way of doing it is working on both of them independently. So you won't start on the left-hand side and hit a roadblock and go, look, I got no idea where this is going. So then you go and work on the right-hand side and you end up at that same point. Well, hang on, if you now know they're both equal to this, they must be the same thing, so you can draw the conclusion, oh, well, therefore this must equals that. But what you never ever do is solve like an equation. You don't start with what you're trying to prove and then say, I'll tell you what, I might cross multiply here or something like that, because if you're doing that, you're assuming that what you're trying to prove is correct, but you're trying to prove it's correct. You can only start with a known fact. And that's why I just started with the left-hand side. I didn't say it was equal to anything. I just started with a piece of algebra. And then I said, right, I'm going to show this is equal to something. By starting with this equals this, we're saying, hey, this is a fact. Well, if it's a fact, why do I have to prove it? Another way I could have done it, as I say, I could have started with the right-hand side. Let's do it that way then. If I had decided I want to start with the right-hand side. The nice advantage with these, prove that, at least you know where you're heading. And I knew I had to have tan on the bottom of the fraction, so I went, all right, let's put tan on the bottom of the fraction. It creates the square as well. It satisfies two things that I need. The tan squared I then can change to sec squared minus 1. And then, if I multiply top and bottom by 2, I get the left-hand side. Not the best way, I think, of doing that one, but of course you could, if you wanted to. Now, there's another idea where you change what it is you're trying to prove. And a really common idea with proving, maybe more so with inequalities than equalities, is to move everything to one side and play with that piece of algebra. So what I'm going to do is I'm going to try and prove this expression instead. Now, this is what I'm trying to prove, so I can't assume it's true, but now I'll just start with that piece of algebra. And hopefully I can show this is equal to 0. It's a bit of algebra, so let's do it like an algebraic fraction. I'll create the denominator 4 tan alpha. Top of the fraction then becomes 2 sec squared minus 2 tan squared. Well, the sec squared I know is 1 plus tan squared. Oh, that turns out to be 0. So now I've proven this new thing. I can say, well, now I know that that's true, then I can move that over, because now it's a known fact. I've proven it to be true, and because it's a known fact, now I can treat it like an equation, and I can move the tan alpha on 2 to the other side. So a very common idea with inequalities, but can be used for proving identities as well. Sometimes that's an easier approach. Let's play. Trig identities, they're fun. They're really fun. Okay.